So here we have the review quiz for chapter 5, and this is all about probabilities. You don't necessarily need StatCrunch to do these things, but I can show you a little bit of how you can use it to solve these kinds of problems. What you do want to have is some kind of scientific calculator, preferably some kind of graphing calculator. A good calculator to use for these things would be Desmos, and then just go into scientific calculator here. It allows you to type in your input here, and then you can adjust your input, whatever you need to do. It's a great calculator to use for this kind of work. So for this first problem, we have a probability of a certain a particular hand is being dealt. It's 0.38. Explain what this probability means. If you play the card game 100 times, will you be dealt this hand exactly 38 times? Why or why not? And so probability is definitely not dealing with any kind of exactness. It's about what's on average what you expect. And you always have to think about probability is really only ever, somewhat accurate for large numbers. It still may not be accurate there. You can flip a coin 1,000 times and it can be heads every single time, but it's just highly unlikely to happen. So for this, a probability of 0.38 means that approximately 38 of every 100 dealt hands will be that particular hand. This is what you're kind of looking for. That's what it means for a probability of 0.38. And you will not be dealt this hand exactly 38 times, since the probability refers to what is expected in not the short term, but the long term. So I believe B is our correct answer. Yeah, probability means that exactly 38 of 100. No, definitely not. Probably most likely it will not be exactly 38. So that's what you're looking for. And you always use the 100 because that's like an easy number. 100 times 0.38 is 38. 1,000 times 0.38 is 380. 10,000 times 0.38 is 3,800. But 100 is a nice small enough number that's got a large enough number. It's small enough to be easy to work with, large enough to be somewhat reasonable, but even still, it's always going to be approximate. Let's check that, and it's correct. Okay, Bob is asked to construct a probability model for rolling a pair of fair dice. Okay, we have this outcome. Of course, if you roll a pair of dice, you will only ever get numbers between 2 and 12. There are no other outcomes that's possible. Because there are 11 outcomes, he reasoned the probability of rolling an 11 must be 1 out of 11. So 11 outcomes, 11 is one of them, so 1 out of 11. What's wrong with his reasoning? And this should be somewhat obvious if you know how dice work, right? A 7 in a dice is the most likely outcome. It's because you can get 1 and 6 on the two dice. You can get 2 and 5, 3 and 4, 4 and 3, 5 and 2, and 6 and 1. There's lots and lots of ways to get 7. The only way you can get 2, however, is with two ones, and 12 is with 2 6s. Those are very rare to happen because there's a limited number of possibilities that you can actually get a 2 or 12, but 7's quite frequent. And so what this is telling us is that this experiment does not have equally likely outcomes. 7 is much more likely than 2 and 12. And in fact, the better way of doing this is to show a table of all the dice rolls. Let me show you that in a moment. What I have here is a table of possibilities for dice rolls, right? This is the actual roll for both in the column and in the row. And the possibilities that you actually get from the roll is going to be inside this table. So 2 through 12, starting here and going on up. So if you get a 1 on the first roll, then we can have these 6 possibilities for the total dice roll. And as you can see, if I look down one of the diagonals here, 7 shows up the most, 6 times. So 7 is weighted far heavier than something like 2 and 12. Those are only showing up once on there. So really this kind of probability, you should think of it not as one-dimensional where you have two dice you're rolling. It's really a two-dimensional kind of thing. And there's 1 through 6 and 1 through 6 possibilities. That creates a space of and a sample space of 36 possibilities. There's not 11 possibilities. There's 36 of them. And just some of them happen to be the exact same thing. That's kind of the idea you want to think about here. Okay, let's check our answer. And that's correct. Okay, the next problem. We have a sample space of 1 through 10, and suppose the outcomes are equally likely, which is not the case for the previous problem, right? And we have compute the probability of an even number less than 9, and what's an integer or a decimal. So we have a possibility, a sample space of 10 possibilities, so we know it's going to be division by 10. And we want the probability of the event E is an even number less than 9. So what even numbers are less than 9 in our actual sample space here? We have 8, 6, 4, and 2. 10 is not less than 9, so we do not include that. We have 8, 6, 4, and 2. That's 4 possibilities. So we have 4 possibilities out of the total 10 that are actually there. We have a probability of 4 out of 10. It wants a decimal, so we're going to go 0.4. And that's correct. So the main idea here is just think about the definition of a probability. And it is in the textbook, right? We have computing probabilities in classical method. The number of ways E can occur is on top. The number of possibilities is on bottom. So that's what I was just using there. Bag of 100 tulip bulbs purchased from a nursery contained 25 red, 25 yellow, and 50 purple. What's the probability that Ryan selecting a tulip bulb was red? So there's 25 red tulip bulbs, so that's the 25 that we want. And the possibilities is, of course, there's 100 total possibilities. So the probability of a red tulip is going to be 25 out of 100, or 0.25. What's an integer or a decimal? So that's what I'm going to do in there. We'll check our answer at the end of it all. The randomly probability of a purple tulip, well, there's 50 possibilities that we want, 50 purple, out of 100 possible. So 50 over 100 is going to be 0.5. And now we have, if 100 tulip bulbs were sampled with replacement, so with replacement means that each time you sample it, the probability is the same. If it was without replacement, you're changing the probability each time. So with replacement is an important one here. One would expect exactly, no, we would never expect exactly anything. So we know it's going to be B. If 100 times it was sampled 100 times, then we would expect about 25 of them to be red and about 50 of them to be purple. That's what we would expect. That may not happen. It may be 100 of them are red and 0 of them are purple. It could be the other way around. It's highly unlikely that that would happen. All right, that one's correct. Let's move on. Probability experiment is connected with a sample space of 3 through 14. Yeah. And the event F is 6, 7, 8, 9, and 10. So there's 5 possibilities there. And G is 10 through 13. There's 4 possibilities there. The sample space has, let's see, 3 through 10. 12 possibilities. There's 5 in F and 4 in G. Assume each is equally likely. List the outcomes in F or G. Find probability of F or G by counting the number of outcomes in F or G. Determine F or G using the general algebraic rule. So list the outcomes in F or G. The outcomes in F or G, so it's going to be 6, 7, 8, 9, 10, 10, 11, 12, 13, 14. The big thing here is that F and G both have 10, so you're not going to count that twice. It's 6, 7, 8, 9, 10. There's 5. We already counted 10, so it's going to be 6, 7, 8. There's 8 possibilities in F and G. Oh, so let's list the outcomes. The list the outcomes is going to be 6, 7, 8, 9, 10, 11, 12, or 13. So the probability of that is going to be, let's see, like I said, there's 8 of them. There's 12 total. 8 out of 12 is going to be divided out. It's going to be, what, 2/3? So it wants 3 decimal places. 0.667 is 2/3. Determine F or G using the general addition rule. Now the general addition rule, let's find that in the text. The general addition rule right here says probability F of E or F is probability of E plus probability of F minus when they can overlap or when they're both true. And really what you're doing here is you're adding up all the possibilities of E and F, but here you've double counted the times that E can happen and F can happen here, and the times that E can happen and F can happen here. So you've double counted that, so you have to subtract one off, and that will give you to the correct possibility. And that's what we see here in this problem that we're working on. The probability of F or G, right, they're not disjoint. If they're disjoint, you don't have to worry about this and case. But they're not disjoint. 10 is in both. So they're you have to use the general one. So the probability of F is the first one. Probability of F is, let's see, that's going to be 5. Around to 3 places. So it's going to be 5 out of 12. Let's see, it's 0.416. So it's going to be 417. The probability of G is going to be 4 out of 12. That's 1/3, so 0.333. And the probability of F and G is the only time that they're both the same is 10. And 10 is there's only one possibility there. 1 out of 12 is the probability of that. So it's going to be 1 out of 12, 0.083. And now we can just combine these things and actually find the probability. So we have 0.417 minus, or that's plus 0.33 minus 0.83. 417, 333, 83. 0.083. And that's going to be 0.667, which looks to me like 2/3. All right, let's go ahead and check that. And that's correct. So, of course, the better way of doing this is to actually have the probabilities added up. So you could do, the first one was 5 out of 12 plus 4 out of 12, which is 9 out of 12, minus 1 out of 12, because that was for the other case. So this is really the same thing as 8 out of 12, or 0.6, repeating. Okay, a probability experiment is conducted in which the sample space of the experiment is this guy here. Is that 12 again? 6 through 10 is 5. 6, 7, 8, 9, 10, 11, 12. Yep. Let event E be 7 through 11. That's 5 possibilities. So 5 out of 12 would be the probability of E. Assume each outcome is likely equally likely. That's going to be 5 out of 12. List the outcomes in E complement and find the probability of E complement. Now, E complement is everything that's not in E. So if 7 through 11 is in E, that means E complement is going to be 6, not 7, not 8, not 9, not 10, not 11, 12, 13, 14, 15, 16, and 17. That's E complement. And that, of course, is going to have 1, 2, 3, 4, 5, 6, 7. There's 5 in E, so there's going to be 7 in E complement since there's 12 total. 12 minus 5 is 7. And 7 out of 12 is our probability. Of course, you can just calculate that. 0.583. That's correct. Probability of E is 0.45. Probability of E or F is 0.6. Probability of E and F is 0.1. So find the probability of F. Now this is going to use the general addition rule like we saw before. So we had the probability of E or F is probability of E plus the probability of F minus the probability of E and F, or the overlap between them. Well, we know some of them, right? We know Probability of E is 4.5. Probability of E or F is 0.6. E or F is 0.6, and E and F is 0.1. And it's asking us to find what's the probability of F. So all we really have to do is get F by itself. I can combine the 0.45 and the 0.1. This is supposed to be a minus, and now I can, it's a plus here. 0.45 minus 1 is positive 35. Now I can subtract that over. Minus 0.35. I get 0.25, the probability of F. Okay, let's check that. And that's correct. Okay, can be the probability a random selected person does not have a birthday on October 10th. So probably any one person has a birthday on October 10th is going to be, of course, the possibilities that there are. Well, there's only one possibility, October 10th, out of the total possibilities of the sample space. Now we're talking about birthdays, so we're talking about days in a year. Let's just use 365 for the birthdays, for the amount of days in a year. We're also excluding leap years, so we're not going to really worry about that. So let's just say there's 365 days in a year. And if we're looking for October 10th, so it's going to be 1 out of 365 days. What's that as a decimal here? 0.0027. So 0.003. Okay, the probability that a randomly selected person does not have a birthday on the second day of a month. So probably does not have a birthday on the second day of the month. So how many second days a month are there? There would be 12 of them, right? Because each month has a second day. So 12 out of 365. Those are what we don't want. So we're going to remove those from what we can have. Now, you could, of course, just take 12 off of 365, or if what we don't want is 12 out of 365, then what we do want is going to be the complement of this, so 1 minus that. That's the same exact thing as, let me just hit enter here. That's the same exact thing as saying, well, 365 minus 12, that's something we don't want. We want 353, so we're going to go 353 out of 365. And you can see here that this is the same as 1 minus 12 out of 365. This is using the complement probability. This is using the actual probability. Both of them give you the same answer. Sometimes it's easier to think about what you don't want and remove it from what you do, or from the total possibilities, which is always 1 for probability. So 0.967 is what we're looking for here. Okay, the probability that a randomly selected person does not have a birthday on the 30th day of a month. So how many months have 30 days? Well, if you count them through, the only month that doesn't have a 30th day is February. Instead of removing 12 days, which would be every month, we're going to remove 11 days since February doesn't have a 30th day. So it does not have a birthday on the 30th day of the month. So there's going to be 11 that we want to remove. The same thing as saying either 365 minus 11 and 354. The probability of that is 354 out of 365. Or we can do the same thing as saying 11 out of 365. That's the probability of that one. Just taking 1 minus that. And you can see we get the exact same answer either way. So the probability that someone doesn't have a birthday on the 30th of a month is 354 out of 365, or 0.969. That needs to round up, so 0.970. Okay, the probability that a randomly selected person was not born in February. Well, February on a non-leap year, right, has 28 days in it. So really all we're doing here is taking those 28 days out of the year. Once again, there's two ways we can do this. There's 28 days in February, 365. That's the probability that a person has a birthday in February. So for probability for a person not having a birthday in February is going to be 1 minus that. You could also just take 365 minus the days from February and then divide that by the total possibilities. And once again, you can see that these are the exact same probability. We get 0.923. Okay, let's check the answers here. All right, let me see what I did wrong. I think I see it here. I think it's just part A here. Probably a randomly selected person does not have a birthday on October 10th. I wrote the probability that they did have a birthday on October 10th. So you want the opposite of this, the complement of that. So we're going to go 1 minus 0.003, and that would be 0.997. Check that. And that's correct. So yeah, once again, we're talking about the probability that somebody does have a birthday on October 10th is 1 out of 365, or 0.003. And we don't want that. So we do 1 minus that. Okay, let's move on. According to a survey, the probability that a randomly selected worker primarily drives a van is 0.872. Public transportation is 0.041. Okay, so what is the probability that a randomly selected worker primarily drives a van or takes public transportation? So the way you're going to do this is you're going to ask the question, are these mutually exclusive? Can someone drive a van and take public work or public transportation to work? And the answer is no. You cannot have both of them, because if you're taking public transportation, you're not driving a van, right? And vice versa. So these are mutually exclusive events. Therefore, if we're going to do an or probability like we are in this first case, all we have to do is add the two of them together. So 0.872 plus 0.041. That's going to give us 0.913. Okay, what's the probability that a randomly selected worker primarily neither drives a van nor takes public transportation? So this is the same thing as saying who's left, really. And so you can think of this as, well, this is the complement of a previous probability. So all we have to do is do 1 minus 0.913. That's going to be 0.87. Sorry, 0.087. That should add up to 1, 0, 1. Yeah. Okay, what is the probability that a randomly selected worker primarily does not drive a van to work? So does not drive a van, right, is the complement of driving a van. So 1 minus 0.872. Can be 0.128. Okay, can the probability that a randomly selected worker primarily walks to work equal 0.15? So walking to work is going to be neither driving a van nor taking public transportation. And so if they can be neither driving a van or taking public transportation, we already know that the probability of that is going to be 0.087. So if we had a 0.15 probability that a worker walks, then that means that we're going to have 0.15. Let's just say that there's only 3 possibilities, right? They drive a van, they take public transportation, and they walk to work. Then the total probability of everyone together, like of all the possibilities of those 3 things, if that were all the possibilities, it has to equal 1, because probabilities can never be more than 1. 1 is always happening. So if you're going to say probability of driving a van or public transportation or walking to work is going to be all those things added up. Let's go ahead and do that. We have 0.872. That's for driving a van. Then we have 0.041 for taking public transportation. And it said, could the probability of walking to work equal 0.15? And there you go. This is already breaching the rule that probabilities can never be more than 1. So we know that that's impossible. So no would be greater than 1 if that were the case. So it could be 0.087. I mean, it could be less than that if people do something other than walking as well, than driving a van or public transportation. So it definitely cannot be 0.15 though. And that's all correct. Okay, 382 undergrad students. Satisfaction with student government, and we have a table of what they had said. If a survey participant is selected at random, what is the probability that he or she is satisfied with student government? So if a survey participant selected at random, what's probably that they're satisfied? So they're satisfied with student government. That's going to be the total satisfied. That's going to be this total right here, right? It doesn't matter what grade level they're in. All that matters is the total that are satisfied. We're not concerned about, or we don't want neutral and we don't want not satisfied. We want satisfied. So 229 is the possibilities, and over 382 are the total. So like if you go count all these numbers up here, you're gonna get 382. The same thing as just totaling them this way and then adding them going down, or totaling them this way down the columns and then adding them go across. You get 382 no matter what. That's the total possibilities or total people that were surveyed, as you can see here again in the question. So the probability that someone is satisfied is going to be 229 out of 382. Let's go ahead and calculate that. Make sure I got those numbers right. 229, 382 is 0.599. Okay, if a survey participant is selected at random, what is the probability that he or she is a junior? So selected at random, what is it, a junior? We do not care about if they're satisfied, neutral, or not satisfied. We only care if they're junior. And if you count that down the junior column, you're gonna get 92. So 92 of the people that were surveyed were juniors. So 92 out of 382 is the total probability of them being a junior. So 92 out of 382, and we get 0.241 for 3 places. 0.241. Okay, if a survey is selected at random, what's the probability that he or she is satisfied and a junior? So we know it's going to be satisfied and a junior. There's only 63 of them that were surveyed. So 63 out of the total, which is 382. .165. Okay, if a survey participant is selected at random, what is the probability that he or she is satisfied or a junior? So satisfied or a junior, and this is the key thing to note, that when you're reading the mathematics, typically any kind of statistics or mathematics, your words matter immensely. You need to be careful with what you're saying. So here we have that he or she is satisfied or a junior. So we care about being satisfied, care about being a junior, but you can see there are people who are satisfied and junior. And so we're going to overcount if we just consider the satisfied, which is 229, and the junior, which is 92. So what we need to do is do satisfy is 229 plus 92, but then remove the and. That's why they had taken you through these steps here. Really what we're doing is we're taking this one plus this one and subtracting out this one because it overcounts too many. And that's what it is, probability of satisfied or a junior. So let's go ahead and find that. That's going to be 0.599 minus 0.241. Or that's right, that's plus. So this first one was, I believe, a junior. This one was satisfied. This was a junior and satisfied. So we're going to go first plus the second and subtract off the overlap. That's going to be 0.675. Okay, let's check it. That's all correct. In finance, one example of a derivative is a financial asset whose value is derived from a bundle of various assets such as mortgages. Okay, we have a randomly selected mortgage has a probability of 0.09 of default or not being paid. So what is the probability that a randomly selected mortgage will not default? So if it's got a probability of 0.09 to default, then for it to not default would be the complement of that, or 1 minus 0.09, 0.91. What is the probability that 4 randomly selected mortgages will not default, assuming the likelihood of any mortgage is independent, meaning that it's always going to be 0.09? So a derivative might be an investment that only pays when all 4 mortgages do not default. Okay, that's just a minor note there. So we have 4 randomly selected mortgages will not default. Well, the probability of 1 mortgage not defaulting is 0.91. The probability of 4 of them not defaulting is going to be... So for this, I just want to go back to the book real quick here and look at the multiplication rule. And the key thing here is that the addition rule, the general addition rule, works for mutually exclusive events. The multiplication rule works for independent events. In other words, the probability of one does not affect the probability of another. So when you have the probability of 2 things happening and they're independent, then what you can do is you can multiply the probabilities together. And that's what we're saying here is the case. We're saying that the likelihood of any one mortgage being paid off is independent of others. So really, if we have 4 randomly selected mortgages that will not default, and if 0.91 is the percentage or the probability that a single one will not default, then that means for 4 of them, it's going to be 0.91 times 0.91 times 0.91 times 0.91, 4 times total. So we could do that as 0.91 times 0.91 times 0.91, or we can just do 0.91 to the power of 4. Same exact thing. So it should be a probability of 0.686. Oh, it wants 4 places. So let's go 6857. Okay. What is the probability that the derivative from part B becomes worthless? That is, at least 1 mortgage defaults. Well, we just found the probability that 4 will not default. So the reverse of that, the complement of that, is at least 1 defaults. So that's the key thing to understand what you're looking at. And can you think about the probabilities in terms of words? Because this one's quite easy to find. All we have to do is do 1 minus the previous one. But you have to understand what you're finding to know that. Okay, so what we got to do is do 1 minus, and there we go, 0.3143. I think it's going to round to 4 places. 3143. And that's all correct. So this is a common thing to have, is like four things to happen in a row, or 5 things, or 8 things, or whatever. And then it asks if at least one does the opposite. In this case, does default, or will not be paid off. that's when the complement 1 minus will help out. Okay. Ari loses 27% of all chess games. What's the probability that Ari loses 2 chess games in a row? Well, 27. Ari loses 27, right? That's 0.21, or sorry, 0.27. So 2 chess games in a row, it's going to be 0.27 times 0.27. So what's the probability of losing the first game? 0.27. What's the probability of losing the first game and the second game is 0.27 times 0.27 because they're going to be independent. So 0.0729. Okay. What's the probability they lose 6 games or 6 chess games in a row? Well, we already know it is. It's just going to do 0.27 to the power of 6. And it's going to be times 10 to negative 4. That's scientific notation. So we're going to go move the decimal point back 4 places. We point, let's see, 1, 2, 3. Yeah, 0.00038 or 0.0004. What's the probability that Ari loses 6 chess games in a row, but does not lose 7 in a row? I can ask the question, what's the probability of Ari loses 7 games in a row? That would be the exact opposite of what I want to find here, right? Because they say, what's the probability they lose 6 in a row, but then not the 7th? Though, if I can find the probability that they lose 7 in a row, and then find the complement of that, that would be our answer. So let's just do that. We know that losing 7 games in a row is the same thing as this to the 7th power. And all we have to do to find the complement is do 1 minus this. And there we go. We have 0.9998. It says 4 places, so that would be 0.9999. Highly unlikely to not happen. So this is going to be pretty much guaranteed to happen. Check that. Okay, let me see what I did wrong here. Okay, the problem wasn't with the last problem. What I had found wasn't quite what we were looking for. What I had found was that the probability that Ari does not lose 7 games in a row. What they are asking for is what's the probability that Ari loses 6 games in a row, but not the 7th. So what I found was that what's the probability that Ari doesn't lose 7 games in a row? That means she could have won the first one, the second one, the third, fourth, fifth, sixth, or the 7th. She could have won any one of those. But here the question is asking specifically that the first 6 games are losses and the 7th one is a win. What's the probability for that exact case? That's the key thing here. And to do that, really what you're doing is you're taking independent events for the first 6, right? First 6 are losses. 0.27 times 0.27, 6 of those together. And the last one is not a loss. It's going to be 0.73. 0.73 is because if she loses 27% of all chess games, that means she wins 73% of all chess games. So the last one's going to be 0.73. So that's what I have here in my calculator. This is if, of course, she loses everything, but we're looking at this one right here. This is where she wins the first 6, but loses loses the first 6, but wins the last one. And that you can see is 0.0002 or 3 when you're rounding up. And that's what I have here. If I check the answer, it is correct. Okay. We have driving fatalities for a certain age and gender. Then we have what's the probability that a randomly selected driver fatality who was male was 35 to 50 years old. Now I'm going to open this in StatCrunch. What is the probability that a randomly selected driver fatality who was male was 35 to 54 years old? So first off, we need to know the total fatalities, right? And that's going to be the sum of all these numbers together. And then we're looking specifically for male and 35 to 54. Or no, it says who was male was 35 to 54 years. So we're making a condition on our probability, or they are not independent. And that's the key thing to note there. Let me show this in the text here. This is the conditional probability rule. It says if E and F are two events, then the probability of F given E, that's what this is read as, F given E, or like in our case, probability of age, I think it was 34 to 54, something like that, given that they were male, was the probability that they're both E and F happen, and the probability that E is there. So E is the one thing it's given. So in our case, it is given that they're male. That's what we're looking for. So we need to find these two things to find the conditional probability. All right. To do that, let's actually open StatCrunch and do some calculations here. So first off, I want to figure out the total. So I'm going to do that down here. I'm going to do edit, or say data, compute. I'm going to compute an expression. And I'm going to build the expression by using the two rows. So we have the male column and the female column. Typically, StatCrunch works by columns. So I'm going to do, I'm just going to sum up all the numbers in the male column and then add that to the sum of all the females. So if I hit OK and hit compute, we have here is the total number of everything here. We've summed up all the way down here, this entire column, and I've summed up all of these numbers here. Now, what we want to do is we want to find the probability that a randomly selected driver fatality who was male was 35 to 54 years old. So this is the conditional probability rule. And we know that we have the probability of 35 to 54 years old given that they were male. Going to be the probability of both. Over the probability that they were male. Now, we have to find the probabilities for both of these two things. And the first one, probability of 35 over 54 and male, is going to be this exact location where we have the probability of male and this one. So it's going to be this exact number here, 11,824. And that is going to be divided by the total possibilities, right? In other words, this sum up here, 55765. That's the probability that goes in this first spot. 11,824, 55765. So that's the top probability. The bottom probability is male, and that's going to be just the sum of these numbers here. So really what I want to do is I want to do data, compute expression. I'm going to do the sum of all the male values. Compute that. And actually put it over here. It didn't put it down there. I put it, and there's 40,351 values in there that were noted. So the probability that is male is going to be this number divided by the total number, 4351 divided by the total again, because you're always doing probability, right? Is just the number of desired outcomes over total outcomes possible. Here we have division by a fraction, and you can see that really what happens is that the total number multiplied by the reciprocal these numbers cancel. And all we have to do is take the number, the probability, possibilities that the driver was 35 to 54 and male, and divide it by just the total number that they are male. Okay, let's go ahead and do that. And I get 0.293 for that probability. Okay, what is the probability that a randomly selected driver fatality who was 35 to 54 was male? So now we're doing the other way around. So we're given that they were 35 to 54, but now they're male. So we can use the same exact idea to do this. But now we're going to flip the two of them. So now it's the probability of male given that they were 35 to 54 years old. And really, what we've learned from this previous one should tell us what we need to solve here. So really what we need to do is figure out how many people were the number of, I should do it like this, number that were male and 35 to 54. And we already have that number, right? That was the exact same number as this one. That came from here. And then the other one is the number of people that are 35 to 54. And that's going to include both men and women. So that's what's going to be changed here. So the first one's going to be 11,824 divided by the number of people that are 35 to 54. So that's going to be the sum of these two here. So in other words, we're going to compute data. We're going to do 11,824 plus 4,733. And that's the number of both male and female that are 35 to 54. 16,557. We get 16,557. And there's a probability. So now we can actually compute this. And we get 714. Is a victim of a fatal accident age 35 to 54 more likely to be male or female? And of course here, they're more likely to be male because 35 to 54, right, has a 0.714 chance of being male, which is higher than 50%. So more likely to be male because the probability is greater than 0.5, which would be like 50-50, equally likely to be male or not, or to be male. Okay, let's check that. And that's all correct. Okay, last one. Due to a manufacturing error, 6 cans of regular soda were accidentally filled with diet soda into an 18 pack. Okay, so 2 cans are randomly selected. The probability that both are diet. Now, if 2 cans are randomly selected, we're not going to put the cans back in there when we do the second selection. So this is going to be without replacement. And that's the key thing to note here. So let's think about the probability that they're both diet. So think about the first can that's drawn, right? There are 6 cans that are diet soda out of an 18 pack. So 6 out of 18 is the probability that your first can is going to be selected to be diet. So you take that out, and now what's the probability of the second can being diet? So what we have here is 6 out of 18, and we're going to multiply this because these events are in succession. We're going to multiply this by, now there's only 5 possibilities because we've already removed one. And now there's only 17 total cans available from the 18 pack. So this is our new probability. This, of course, can be reduced. This is just 1/3. And we get 5 over, let's see, 30 and 21, so 51. That's the probability that both cans that you select are diet soda. Okay. .0980. 0.0980. Determine the probability that both cans contain regular soda. So here we're talking not about diet cans, but regular. And so there's 12 out of 18 for the first pick, and the second pick is going to be 11 out of 17. And once again, we've already taken one can out, and so there's only 17 possibilities. And the one can we took out was a regular soda, so 12 becomes 11 now. That, of course, reduces down to 2/3. We get 22 out of 51 for our probability. And this gives us 0.4313. Okay, would this be unusual? Yeah, because it's less than 50%. Determine the probability that exactly 1 is diet and exactly 1 is regular. So when you're drawing 2 cans out of there, there's 2 cases, right? The first one could be diet, the second one regular, or vice versa. The first one is regular, the second one is diet. So we're asking really, what's the combination or the sum of these two probabilities, these two events that might happen? So the first one being diet is going to be 6 out of 18, and the second one being regular, because exactly one's diet, exactly one's regular, is going to be 12 out of 17, right? The first one being diet means we take one can out. So when we take a second one being regular, we only have 17 possibilities because we've already taken one can out of the total 18. But 12 still remain that are regular. Since the first one was diet, the 12 still remains. This is going to be added to the first one being diet. Sorry, the first one being regular, and the second one being diet. So same idea here, where we have 12 and 6 are the total number of diet and regular in there, but we reduce by 1 on the denominator because we've already removed a can. So these are 2 possibilities. They actually end up being the exact same thing, right? I can rearrange things around easily. Here I get 3. This is going to be 2. This becomes 2 and 1. So it's going to be 14 over 17. This one does the exact same thing, right? This is going to be 2 over 3. This is going to be 1 and 2 here. So we get 4 over 17 plus 4 over 17. That's a probability. 8 over 17. 0.4706. All right, let me see what I messed up on. Okay, I had a rounding error there. This is just 4314. And would this be unusual? The answer is no. It's unusual if it's less than 5%. But I was thinking 50%. It's 5%, not 50%. So, but check the answer there, and that's all correct.